The first chapter we cover in this class is chapter 13, utility systems. The thing about utility systems is they're not tied to necessarily one particular process. If you think about electricity coming into your house, you think of that as a utility. That powers all kinds of different things in your house, whether it's in your kitchen or laundry room or office. You know, that electricity goes to all over the place in your house. Natural gas might come into your house. Use it for cooking on the stove, the oven, heats your home, hot water heater. Utilities like that are the same in the process industry. The utilities we're going to talk about today aren't tied to one specific process. Okay, they go all throughout the plant. So the first one that we talk about in this chapter, the first system is utility systems, which go over all these different types of process systems. So reactors we talk about in chapter 14, then 15 is distillation. Then we get into 16 with the rest of these. They all rely on utility systems. So if your utility systems go down, then all these other process systems will go down as well. The first one that the book kind of talks about and lays out is steam generation. Steam we use for heating, we use for turning turbines at different places. We'll get into this more in detail later on in the chapter, but we're going to have a boiler that's going to create the steam. We learned about that in equipment class. We have a header system that's going to distribute the steam all throughout the rest of the plant. Condensate return and a deaerator, and we'll talk about those a little bit later in this chapter. This is how the American Petroleum Institute API distinguishes steam, classifies it in different pressures, super high to medium to low. Condensate recovery is that steam that's already been used up, it's already gotten all its heat out of it, and it turns back into its liquid form of water. Notice that there's some gaps in this because these are just kind of relative. There's no, there's a gap between 200 and 400. The steam that we're going to see in the labs today is actually 150, so it's somewhere in between this medium and low pressure steam category. These are just general terms for what they use all throughout different refining and chemical processing. One of the main process utility systems that comes in is water. Okay, we use water for all kinds of different things, including turning it into steam, like we just talked about. We also use it in these other ones as well. Raw water is just like it sounds. We bring it in from a municipal source or a river or possibly a lake, depending on where we happen to be, and we use it all throughout the plant. We'll filter it, we'll do some different things to it, we'll treat it, we'll talk about that in the labs, and we'll show you some of the water treatment that we do in the labs, but that's just our main source of water coming in to the plant. Fire water systems, fire water is fire prevention, basically. They're sprinklers. They're to put fires out or control or maintain fires. So they're separate. We don't usually treat that water very much. We just have it on reserve, usually around 100 psi, put into lines, and then ready to go. We usually have backup power for that. A lot of times it's a diesel generator, so that even if we lose power, so if we think we have a really catastrophic earthquake, thunderstorm, if we're down in the Gulf area, a hurricane, we could lose power. We could still have a fire in that case, and we want to be able to put the fire out, so we always have backup systems for that. So you'll see that it's separate from a lot of the other water systems. Boiler feed water, we get into that in more detail, but basically we take water in, we're going to treat it, we're going to make sure that we filter it, make sure that we get any of the mud, clay, silt, sand out of it, and then we're going to treat it to it doesn't corrode our pipes. Okay, if we put that just regular tap water into our pipes, it's going to be looking for minerals. It's going to be wanting to corrode our pipes, and so what we do is we add some minerals to it to prevent that from happening. Cooling water systems, we talked about a cooling tower before, and so we just have to treat that water similar to the boiler feed water. add some anti-corrosion chemicals to it so it doesn't corrode our pipes, and we can run it through a cooling water system. And then after the boiler feed water, we get into the steam systems like that. Again, this is just kind of what we already went over, raw water and fire water. We talked about that. They're automatically going to start up. The fire water, we'll show you what that looks like when we get into the labs, how it looks, separate valves, automated valves that are held closed. The valves are closed by just either a thin piece of lead or a gas-filled glass tube, and when those either melt or break, then the water is going to come out of these lines and the pump's going to kick on. Okay, and they melt or break due to heat, due to a fire. Okay. Next part of this is getting into steam and boilers and how we kind of treat it, and this is showing us an example of why we use it. There's a lot of heat in water. There's a lot of heat storage capacity in water. What we have is we measure the amount of energy in BTUs, British thermal units. What a BTU means is how much energy does it take to raise 1 pound of water by 1 degree Fahrenheit. Okay, 1 BTU will raise 1 pound of water up by 1 degree Fahrenheit. Okay, but so as we go from, say 50 degrees here, 50 degree water, to heat it up to 100 degrees, it would take 50 BTUs, okay, for 1 pound of water. Now, where we get into steam, it takes 970 BTUs to turn 1 pound of water into 1 pound of steam. As you notice, this line goes horizontal right here, and you can follow along on page 340 in your textbook. We heated up the water to 212 degrees. That is just water at 212 degrees. And then to turn that water into steam, notice the temperature does not rise. The temperature stays flat, but it turns into steam. And a good example we like to talk about this is if you've ever made spaghetti or macaroni and cheese on a stovetop, you bring that water up to boiling, that water gets up to 212 degrees, you start to see the bubbles form, right? But it takes a long time then for all of that water in your pot to actually go away, to actually turn into steam. And all that time while it's boiling, you're putting heat into it, you're putting energy into it. And where is that energy going? It's turning that water into steam. We call this here, these horizontal lines, latent heat. Okay, latent heat, different than sensible heat. Sensible heat right here, we can sense it with the thermometer. If you were to put tap water into a pan, be about 60 to 70 degrees, put it on the stove, and you put a thermometer in it, you're going to see that thermometer rise. And that thermometer is going to keep rising up 100, 180, 190, get up to 212 degrees. And once it hits 212 degrees, you're going to see it start to boil. As it boils, you're going to see bubbles form, releasing the liquid water into steam, but that thermometer is still going to show 212 degrees that whole time because the water that it's in is 212 degrees. And the same is true when we have this ice melting and liquid freezing. Anything below 32 degrees, we have ice. Anything above 32 degrees, we have liquid water. But during this time, this transitional period, it takes 143 BTUs to be able to turn that cold water into ice. Okay, now why this is important is if you notice, heating water up itself does not take that many BTUs. Turning it into steam takes a whole lot of BTUs, 970, a whole lot more comparative than the 180 it takes to get up from 32 to 212 degrees. That's, heat is not lost. That energy is saved in the steam, and when we run it through the system and we condense it, turn it into condensate, we get that 970 BTUs back. So it's a tremendous amount of energy that we have stored in the steam. Okay, in order to put water into a boiler to turn it into steam, we have to get rid of the impurities. We have to add chemicals to prevent corrosion. We go through coagulation and flocculation. We'll talk about those more in the labs. You'll be able to see that. Basically, we're taking small particles and jamming them together, making them bigger so that we can then pull it out and be able to get rid of it. We have some demineralization, demin water, we call that. We'll show you what that ion exchange process looks like. We can use demineralization to get rid of those harmful impurities in the water that could cause problems with our system. We need really clean, pure water to go into a boiler, because if we think back to here, what we're doing with this water is we're heating it up, turning it into steam, then condensing it back down, and then putting it right back in the boiler, heating it up, turning it into steam, condensing it back down. It's just a long cycle. Okay, the same water typically stays in the boiler for a few cycles, and it goes through and keeps going, and so we have to have it really clean because it's going to be in the system for quite a long time. Oxygen, oxygen is bad to have inside of a boiler, inside of the water, and so we have to de-aerate the water. What we do with that, how we do that, is we remove the air out by heating it up. And so if we go back to the spaghetti that we were making, or the mac and cheese that we were making, if you've ever put a pot of water on the stove before and you turn the heat onto it, before it starts boiling, you notice little bubbles at the bottom of the pan. And what those little bubbles are, that's the oxygen being driven out of the water. And if we don't drive them out of the water before we put it in a boiler, it can cause problems with us later on down the system, because it's going to corrode. Right? Oxygen is going to promote corrosion inside of our pipes, so we want to get it out. And the last line here is blowdown. Blowdown is removing water from the boiler system. We talked about this back in equipment class as well. And so as we have that water cycling through the boiler, it's still going to pick up some corrosion. It's still going to have some solids that get through the system, not entirely 100% pure. All of this doesn't work all the way 100%, have pure, clean, 100% water. And so what we do is we take a stream of that water from the bottom of the boiler, and we open up a valve and we dump it down to the sewer system to get rid of it. And that, as we get rid of that little bit of water, it carries with it any solids that may have got carried into the water or brought into the system from either outside sources or from the pipes themselves. As we have bits of corrosion in the pipes, that'll go out down the blowdown. Switching gears here, not heating anymore, now we're cooling. So cooling water system. Typically what we have is we have a induced draft fan cooler, cooling tower. If you see right here, there's a twin fan one, a picture of a twin fan one right here. The one that we're going to look at in the lab is only a single fan, but that just depends on how much air we need to remove. And so when we evaporate water, when we run a fan like this, we evaporate water, then that evaporating water is what we consider an endothermic process, and then that allows the temperature of that water to cool down. And so what happens is that heat that it takes, right, to boil water, if we don't add heat to it and that water evaporates, if we're don't have a stovetop, we don't have a natural gas fire, then what happens is it pulls heat out of the remaining water. So we learned about this, we talked about this a bunch in equipment class, and we'll talk about it in the lab a little bit more as well. But that's what we're doing there. And so as that water goes through, we blow air across of it, or suck air across it, and then that cools it down. So we recirculate the pumps. We have recirculation pumps. They go through. I have electric motor that turns those. You'll see what those look like in the lab. What we have is we have water run through this for 3 to 5 cycles. Okay, the lab we're going to look at, we do it for 3 cycles, and then we have water blow down after that. And so it goes in, it gets added in and as makeup water. It goes through the system 3 times, and then it gets blown down. We use air systems, 2 main things: utility air, in case we're adding air into something in the system, into the process that we need to. We can have it used for decoking furnaces. We have it used for supplying air if we need to blow down things. We'll talk about air uses when we get into the solids handling things, to be able to clear off conveyors, clear out baghouses, do things like that. That's called utility air. Utility air needs to be somewhat clean and dry. We'll show you how air dryers work and that when we get into the labs. Or we have another system that's instrument air. Now, the labs we're going to look at, the instrument air is cleaned and dried, and so we make sure we get any oil out of it. All the air that we bring in has some amounts of humidity in it, and that humidity is moisture, and when we start to compress the air, that moisture will get into droplets, and when we have air and moisture inside pipes, we can get corrosion, so we want to make sure it's dried, especially when we have instrument going to it. And so when we have it going into instruments, the tolerances inside these instruments, inside these control valves are very, very tight. And so any types of corrosion that gets into those would mess those instruments up. So it needs to be clean, dry air. Nitrogen systems, we can use that as a backup for our air. So air compressors, generally high horsepower motors. So either they'll have either diesel powered pumps as backups, diesel powered, compressors as backups, or if we need to back it up with a tank, nitrogen tank, we can. Or another common way that we use nitrogen systems is to blanket vessels. So anytime we have vessels or lines conveying combustible materials, we need to put a nitrogen bed over top of them. That gets rid of the oxygen, and getting rid of the oxygen minimizes our chances of combustion and fire hazards. Natural gas systems. We use natural gas systems. You'll see these in the labs. Fire the boiler. We use these to fire furnaces. We use these to fire dryers. Anytime we need a lot of heat and a quick amount of time, natural gas works well for that. Clean burning. Years ago, we used a lot of coal, especially in this region. Coal fire furnaces, coal fire boilers, but that has started to go away as natural gas became cheaper and cheaper, and the transportation of coal became more and more expensive. It was easier for places and cleaner and cheaper and less maintenance costs to put in natural gas systems. So we see a lot more natural gas systems now, especially in this area, than what we saw 20 or 30 years ago. Also, we use natural gas as a purge medium. So whenever we're starting a system up or shutting it down, you would think we should use like air or something for this, but getting air into natural gas lines and getting air into fuel lines and distillation lines and lines that contain highly combustible materials is not a good thing, because then we're adding air into a system that normally has fuel and normally has heat. And once we get oxygen, fuel source, and a heat source, we have the prime candidates for having a combustion or an explosion. And so if we purge it out with natural gas first, check for leaks, do things like that on startup and shutdown, then we're not introducing air into that already combustible system, okay, that system that already contains combustible materials. Electrical systems, we'll have a lab where we'll show you where this looks like, how we have motors, how we have them designated, how we have them safely be able to shut down with breakers, how they're started and stopped. We'll show you what the motor protection looks like. We have voltage measurements called voltmeters, and we have current measurements when we're actually running, how much energy, how much electrical energy is going through the lines. That's the current measurements. Okay, the voltage is the force of that. Okay, so the higher the voltage, the higher the force of it. Electrical energy, and then the actual flow of electrical energy going through it is the current. We use those together to be able to decide the power going through it. And anytime we start pulling too much power or we start pulling too much current, then we have issues where we could be tripping breakers, blowing fuses, and things like that. We'll show you what those look like in the lab. Keep going on power systems. We have a lot of backup power systems. So we have a lot of diesel powered generators in industry, especially for critical equipment. Transfer switch delivers backup power. okay, to be able to run not as much as what we had been running usually in a production facility, but at least enough to be able to safely shut the unit down. So we'll have a few key critical pumps, compressors, things like that to be able to give us enough power to be able to safely shut things down. We also have in almost all, or basically all production facilities, is uninterruptible power supply, uninterruptible power system, or UPS. And we'll show you what one of these looks like later on in the labs. And what we have here is we have computer controlled equipment, right? Computer controlled automated equipment, inside operators. We've seen what those look like, what those control stations look like. They run on computers. And if you think about your desktop computer in your office or at home, even if you have a momentary little blip of power, so just a fraction of a second, if the power goes out until the time a generator comes on, what happens to that computer? Well, if it's a Windows computer, it's going to go down. It's going to have to reboot. You're going to have to re-log in. You're going to have to restart up. And it's a process that even on a fast computer could take 30 seconds to 60 seconds. So that's a really long time in industry to not have control over your unit. And so what we do in industry is all the operator stations, all the control stations are run on a battery all the time. Okay, so that battery is running them all the time. And that battery is constantly being charged. And so we are constantly being fed through a battery. And then if we do lose power, the computers don't see anything different. They're still running off the battery. The only thing is different is that battery's not being charged right now. And so that gives us anywhere from 1 minute to 12 hours to possibly even up to 24 hours of battery storage charge, so that we can lose power for a little bit and the computer never blinks, never goes off, never does nothing, because it's still running on a battery like it always has been. We'll show you what one of those looks like in the lab, and we'll show you how they can look differently and how they can save us from momentary power losses. The book kind of jumps back to steam systems here. Kind of out of order. We've already talked about steam systems, but the last thing that we go into with steam systems is the steam traps. We'll show you what these look like up close and personal in the labs. Bucket traps or impulse traps work kind of on the same principle, that as the line fills up, what all steam traps are going to do is they're going to stop the steam. So the steam is going in its vapor form. It's going through a line. This trap is going to trap it and stop it, hold it in that line until it converts back into water. And the reason we do that is to get that 970 BTUs of energy out of that steam. If we didn't have these, the steam would just blow right on through and it wouldn't give up any of its heat, or very little of its heat, and we wouldn't get much energy out of it. These two are going to work basically the same way. They just look a little bit different on the inside: inverted bucket or impulse or float. As that line fills up with water, this floats up, and then eventually, once it floats up to the top, it releases the water out of the line, the condensate out of the line, and then falls back down. When it falls back down, it stops the steam again. This works like a thermostat. When it's in the heated up position and it's heated up, it expands, right? So metal can expand and heat when it heats up. And so when it's hot, it'll expand, and when it expands, the valve closes. Okay, so it basically expands into a hole, into a seat in the trap, and then when it expands into that seat in the trap, it stops all the flow. Once that steam flow stops, it starts cooling down and condensing back into water, and once it reaches the temperature of 212 degrees and it's water now, then it will condense, the metal will condense, opening it up, allowing the water to pass through. As the water passes through, steam comes in, heats it back up, and it closes again to stop the steam again. We also put strainers before most steam traps, because the steam traps have very small gaps in them, and so just to allow a little bit of steam to flow through, a little bit of condensate to flow through, and so we have strainers there to keep small pieces of contaminants out of getting into any of the steam traps. Industrial sewer systems, so we have water and process fluids collected. It's going going to go all the way into a separator, and we get that to a plant waste treatment area. And so we have to be specific about where we're going, what we're doing, because we'll also have in facilities storm drains. Storm drains are just made to take rainwater, and storm drains will be led directly into a river or creek, and they won't go through any treatment processes. And it's very important, critically important, that no processed fluids go down storm drains. Okay? They have to be there because we have to get the rainwater out of the facilities and things, but we can't let any processed material go down there. And so we'll have specific industrial sewers marked. Storm drains will be marked. Usually they're painted a certain color, and the industrial sewer systems are painted a different color. And so processed fluids can go down the industrial sewer systems because then they go to a treatment area. And generally speaking, the treatment areas are going to remove hydrocarbons, remove oil phases, remove all kinds of different things, any contaminants that maybe get into it before it goes into discharged back into the environment. Refrigeration system. So we've been through cooling towers. We've talked about that in equipment class. Those cooling towers generally can only get the water down to 90 degrees Fahrenheit. So if we need to go any cooler than that, we go through a refrigeration system, also called a chiller. And here we're using, just like a refrigeration system, just like a air conditioner at your house or your refrigerator at your house, we use a compressor to pressurize high pressure refrigeration gas, and then goes through an expansion valve, and then that low pressure refrigeration liquid is cooled. We can blow air or run glycol water mixture across a heat exchanger, and then that becomes a low temperature way that we can use to cool things. So whatever it happens to be, whether this is going through a air exchanger or a liquid exchanger, water exchanger, and then we have either cooled water, chilled water, or chilled air to be able to use to pull more heat out of the process in case we need to go down below 90 degrees Fahrenheit, which we'll show you one of the labs. We'll be able to see what it looks like, how it runs, and everything like that to be able to subcool material down below 90 degrees Fahrenheit. Last one we have is relief and flare systems. So relief is going to be, and flares are going to take any of the hydrocarbon gases that are either coming off of a distillation column, coming off a storage tank, coming off a reactor. Any of those gases, we can't let it go back into atmosphere. We have to burn it off first. And so we have a flame to be able to burn those hydrocarbons off, to be able to turn them into CO2 rather than have them come off as methane or propane or anything like that that's going to be harmful to the environment. So we relieve them off, and then flare burns them off. We'll show you what the flare looks like in one of the labs, kind of how it does. We'll show you how all the piping kind of connects into all the exhaust piping from the plant, the tops of all the vessels and the columns, exhausts all into one header pipe, and then it all goes into the flare system to be able to safely burn off any hydrocarbons or any pollutants that we have. All right, let me know if you have any questions. We'll see you in the labs.